Nuclear fusion has been a pipe dream for decades, always 20 years away, never 19. It's easy to get jaded about this technology and write it off as impossible, especially when nuclear fission energy already exists and is being underutilized. But, by the end of this video, I hope that I can change that feeling and get you as excited as I am about the potential of this technology. If we, as a civilization, actually pull it off and invent a cost-effective nuclear fusion power plant, it would change the face of society. Clean, safe fuels will allow every country in the world to benefit from this technology, allowing countries around the world to be energy independent, preventing one of the leading causes of conflicts around the world, as we fight for control of energy sources. Cheap, reliable, and abundant energy is the foundation of every sci-fi utopian society. It would solve our issues with climate change, allow us to electrify industries that require fossil fuels, like steel smelting, and create entirely new industries that have been held back by energy costs, like water desalination. Providing the world with fresh clean water to irrigate our lands and turn barren wastelands to fertile pastures. Ushering in an era of clean, safe abundance, a utopian future that has been dreamed of for decades. Nuclear fusion experiments have been underway since the very earliest years of the Cold War, with the first generators firing up in the 1950s in both the USA and USSR. The Soviet Union approached the problem with a tokamak design, while the Americans used a slightly different approach, the stellarator. Each design attempts to solve the same problem. Fusion, in essence, isn't terribly complicated. We can make new elements by combining smaller elements, and in the process, release a lot of energy. However, to successfully combine elements, we need to overcome the electromagnetic repulsion that pushes them apart, like pushing two north poles of a magnet together. Atoms will repel each other. In order to force them together, we need to input a tremendous amount of energy, but we can't just grab individual atoms and force them together like magnets. Instead, we create a plasma, essentially a cloud of charged ions which, thanks to their charge, can be manipulated by a magnetic field. We can then confine the plasma within a magnetic field, preventing the ions from hitting the fusion generator walls, and gradually raise its temperature to extremely high temperatures that would otherwise melt every solid material in the universe. Raising the temperature of the plasma causes the ions to move faster and faster, raising the ions' kinetic energy so high that their speed alone allows them to punch through the electromagnetic repulsion and collide. Both of these designs, the tokamak and stellator, use slightly different methods of magnetic field confinement, generated by massive superconducting magnets, to achieve fusion. The tokamak became the leading design today as a result of a release of information from the USSR on the tokamak design in 1968, which showed a tremendous jump in energy efficiency. However, both designs use the same fuels. The exact reactants we use have a huge effect on how much energy we need to put in and what we get out at the end. Most reactions use two isotopes of hydrogen. A regular run-of-the-mill hydrogen has one proton in its nucleus, with one electron in orbit. We could perform fusion with this kind of hydrogen, but the energy we can extract out of the reaction is very low. Instead, we frequently combine deuterium and tritium together. Where hydrogen normally has one proton and one electron and no neutrons, deuterium has one proton, one electron, and one neutron, while tritium has one proton and one neutron and two neutrons. This combination is used for a couple of reasons. First, it has the largest probability of giving us the exact result we want. Other reactions, like a regular hydrogen-to-hydrogen reaction, have a very high probability of creating helium-2, which is unstable and almost instantly decays into two regular hydrogens again, and releases very little energy in the process. They have a lower probability of combining to form deuterium, the reaction we actually want, which then goes on to fuse to form helium-3 and finally helium-4. This is the reaction chain that powers the Sun, but the Sun has an unfathomable amount of particles, making the probability issue completely irrelevant and the crushing gravity needed to create the conditions needed for fusion. We need to supply those particles and the energy needed to combine them ourselves, and if we can't extract more energy than we put in, that's just a science experiment, not an energy source. We have successfully created many fusion reactions here on Earth. In fact, I witnessed the bright pink flashes of fusion myself while visiting Helion recently. We know how to achieve fusion. The problem we are now trying to solve is lowering the energy we need to input while maximizing the energy we can extract. So, step 1, we need fuels that require less energy input that release more energy. That's where deuterium and tritium come in. When combined, they have a very high probability of creating helium-4 and release on average 17.6 mega-electron-volts, MeV, for each and every fusion event. For comparison, uranium-235 produces about 11.4 times this energy for each fission event, 200 MeV, but on a mass basis, that deuterium-tritium fusion reaction releases over 4 times as much energy as uranium fission, and produces no dangerous radioactive products. Helium is actually quite a useful byproduct, being used to cool MRI machines' superconducting magnets, to fill rocket tanks after their propellant has been expended to prevent them from exploding. And we will eventually run out of the gas, so having a way to make it ourselves would be a nice backup. Deuterium is fairly common on Earth, occurring naturally in seawater, making up about 0.02% of hydrogen in seawater. And because deuterium has an extra neutron, it makes that water molecule heavier, giving it its name. Heavy water. That difference allows us to separate it through a number of means. Vacuum distillation allows us to take advantage of heavy water's higher boiling point, while the Girdler-Sulfide process separates heavy water through chemical reactions. We can then simply electrolyze the heavy water to separate the deuterium. However, one of the issues facing nuclear fusion is the rarity of tritium. Our primary source of tritium is nuclear reactor moderator pools, which are often filled with heavy water. These pools are designed to absorb the high-energy neutrons given off during nuclear fission, and in doing so can become tritium, a hydrogen with 2 neutrons. This source of tritium is becoming less prevalent as nuclear power plants are gradually being shut down around the world due to competition from cheaper forms of electricity. Currently, the total global reserves of tritium are estimated at just 20 kilograms, which is not a lot considering ITER program, the massive internationally funded fusion generator being built in France at the moment, estimates a commercial reactor will need 300 grams of tritium every day to generate 800 megawatts of electrical power. Meaning we would eat through the entire global supply of tritium in just over 2 months. 800 megawatts is enough to cover about 2% of France's peak power consumption. Even if we could continue sourcing tritium from nuclear fission reactors, they only produce about 100 grams each per year. This is a major problem, however we do have a solution in mind. We can use the high-energy neutrons spit out from the fusion reactions to do a bit of alchemy wizardry. When those high-energy neutrons encounter lithium, they can split the lithium into tritium and helium, providing a steady supply of tritium right where it's needed. This is done in what is called a blanket around the fusion chamber. The design of the blanket is one of the most challenging parts of tokamak fusion generator. ITER will test over 180 design variants of this blanket that will line the donut-shaped interior. Because the blanket needs to do a lot more than just breed tritium. It is also where the energy of the fusion reactions gets converted to heat. 80% of the energy of the tritium-deuterium fusion reaction is carried away by those high-energy neutrons in the form of kinetic energy. We need a way to convert that kinetic energy to electricity. As the fusion reaction rages in the center of the magnetically confined plasma, neutrons begin to erupt outwards, unaffected by the magnetic field thanks to their neutral magnetic charge. Tokamaks convert the energy of these tiny particles by slowing them down in the blanket, trading their kinetic energy with atoms in the blanket to heat energy. This heat energy is then captured by high-pressure water being pumped through cooling channels, converting it to high-pressure steam to drive a steam turbine. Humanity's tried and tested method of creating electricity. The material that fulfills this role needs some other unique properties. First, in order to optimize for heating and tritium breeding, we need the material to be a neutron multiplier. When the high-energy neutron from the fusion reaction enters the blanket wall, we want it to strike an atom inside the blanket and release 2 neutrons. creating an additional neutron that allows the blanket to fulfill both roles of generating heat and tritium. Beryllium is currently the leading candidate for this role. When the neutron strikes it, it splits into 2 helium-4 atoms and 2 neutrons, multiplying our first neutron and allowing our blanket to generate tritium and more heat. Beryllium, the same material used for the James Webb Telescope mirrors, is the material of choice because the helium byproduct does not contaminate the plasma, and critically, the material retains little tritium within itself. We need the tritium to naturally escape the metal, partially because we need to collect the gas to replenish our fuel, but also because tritium is explosive, just like normal hydrogen. However, beryllium does have its problems. First, the sheer quantity of beryllium a commercial fusion reactor will require. Current designs call for between 216 to 560 tons. This is an issue because beryllium is extremely expensive due to the limited supply of the material. Annual global supply last year amounted to only 260 tons. The entire annual global supply of beryllium could just about build one generator. Next, there are safety issues. Beryllium can contain large quantities of uranium. China's beryllium blanket module contains 100 parts per million uranium. So, 0.01% of the blanket is composed of uranium. This isn't an issue for most components that are usually made out of beryllium. Like the beryllium, aluminum, copper engine pistons that were banned from Formula One in 2001. However, it becomes a massive problem when the uranium is exposed to those high-energy neutrons. The same kind of neutrons that split uranium in fission reactors. This creates fissile isotopes, or, in other words, it makes the beryllium radioactive. If there were 30 parts per million of uranium to beryllium in a commercial-scale fusion reactor, that would mean there is 17 kilograms of natural uranium and 123 grams of uranium-235, the uranium needed for fission reactors. The byproducts of this uranium would make disposing of the blanket at the end of the generator's life incredibly difficult. This all points to one major problem that I see with tokamak fusion reactors. Even if we manage to reach net energy output, these generators don't solve the biggest problem holding nuclear energy back. Cost. Nuclear fission power is a wonder technology of the last century. It promised abundant, clean, cheap electricity. A technology that we scarcely even dreamed of 2 centuries ago, as we first discovered the existence of the atom. Yet, we are closing down nuclear fission reactors all across the world when we need that clean power more than ever because it's uneconomical. The cost of building a nuclear fission reactor and dealing with the radioactive byproducts when decommissioning it are 2 primary factors making it uneconomical, and tokamak reactors are driving straight towards the exact same economic problem. However, one company is doing it differently, Helion. The company I visited to witness nuclear fusion reactions and interview their brilliant CEO David Kirtley. They are doing things completely differently to everyone else in nuclear fusion research. They aren't capturing energy with steam power, eliminating the need for costly beryllium blankets. They are developing a method of making fuel on site that doesn't require lithium, instead using the cheap and plentiful deuterium to create it during fusion. And they are using a completely different magnetic confinement method to achieve nuclear fusion temperatures.